We've heard gravitational waves are ripples in space-time.
It's very tempting to look out into space and think of empty space. Space isn't empty. Space doesn't do nothing. It can curve, it can ripple, it can tear. And so that's really the wavy part of space-time. And the idea is when we have objects that are massive, things like neutron stars and black holes.
So dense objects in the universe.
Objects that have so much gravity packed into a small volume that really the space around those objects is very bent.
Have those objects tried Ozempic?
This is StarTalk. Neil deGrasse Tyson, your personal astrophysicist. I got with me Harrison Greenbaum. Harrison, how you doing, man?
I'm good. Thanks for having me back. I'm so excited.
I know. This is not your first rodeo with us.
Right.
All right. You know what we're going to talk about today?
Space. Stars.
Okay. Gravitational waves.
Ooh.
Yeah, no.
I know about them separately.
Oh, gravity and waves?
Yes.
But not gravitational waves.
Really
I will
exciting.
totally hook you up on that.
All right, great.
So, Harrison, you're a comedian, and I just learned you have an off-Broadway show.
Yeah, it's called Harrison Greenbaum, coincidentally. What just
Oh, really?
happened?
I wonder why.
Yeah, exactly.
So, Harrison Greenbaum.
What just happened?
What's that? It's on stage and it's
It's a
performance?
comedy and magic show. I've been working on it for
I
probably...
forgot you do magic.
Yeah.
Oh my gosh, that is so geeky.
Oh, yeah. I went to magic camp and space camp, so I've really...
So you had no dates going
That's right,
through your
exactly.
entire career of school.
Yeah, my parents wanted breaks from me 1 week at a time.
So our guest today has a different expertise from you.
Really?
We have Nergis Mavalvala. Did I say that correctly?
Yes,
Excellent. And this is your second time on StarTalk.
it is.
You were last on StarTalk 9 years ago.
I'm hardly 9 years old. Don't
At one of our live performances,
I was.
StarTalk Live, in a Count Basie Theater in New Jersey.
That's
We
right.
occasionally take the show on the road, but regionally.
Nice.
Yeah. And that was back when our first results from gravitational waves came across.
Shortly after the first discoveries.
Yeah, very, very cool. Well, you are a quantum astrophysicist. That is the baddest assest thing you could ever put on a business
I
card.
feel like quantum is very small and astrophysics is very big.
It's another reason why. Quantum. You are a professor at MIT. Which department did they put you in?
Physics.
Physics department. That makes sense, doesn't it?
It would be weird if she was just teaching English.
And I'm sorry to learn you're also dean of the School of Science. Sorry to hear that.
Yes,
Yeah.
Can you get people in trouble?
I can, but mostly I get myself in trouble.
Do you cheat on your own test? Like, I have the answer key. It's not fair.
So, a dean of the MIT School of Science. I say I'm sorry to hear that because that takes time away from like your studies, doesn't it? But they pay you more.
They do.
Yeah.
They do. And the other thing that comes with being dean is you actually get some administrative help. And as a result, I actually have a little bit more time to be in the lab than when I'm just being professor and running around doing too many things.
Trying to get things done. Now you got peeps.
Now I got really, really talented peeps.
Okay. All right. That's how that should work. You are on the LIGO team. Let's test Harrison. Harrison, it's an acronym. What does LIGO stand for?
Lord, I got options. that works?
Nergis, I think that should be the new meaning of the acronym LIGO.
There's a lot of changes coming to NSF proposals. That could be one of them.
Lord, I got options. Laser Interferometer Gravitational Wave Observatory. Did I get that correct?
You did.
Very good. And you're on the team that discovered these. So I understand they took a bunch of people to Stockholm for the Nobel Prize. Were you on that plane?
Yes.
Excellent. So you got all dressed up and everything?
Kind of, yeah. Yeah, no, that's not my
What do you mean,
favorite.
kind of? What outfit would you have for some other occasion if not for the Nobel Prize?
I'm not a dress-up type. And so, and I'm not a girly type. So I had to also decide, am I going to wear like girly clothes or a tux?
Oh, you fell into a haberdasheral gap.
Yeah, yes, a sartorial dilemma.
Okay.
Nice.
Interesting fact there.
So what did you end up doing? Just shorts? I feel like that's the
King of
average.
Sweden was cool with that. You know, no. So I'm delighted that you got to see that. By the way, we just had on StarTalk, I hung out with Kip Thorne, the man himself, and we visited him in his home, and we had a whole interview. It was largely about, he was one of the executive producers on the film Interstellar.
Whoa.
And it just had its 10th anniversary, and it was a re-release just in celebration of that fact, because it had so many people talking about gravity physics and relativity and all the rest of that. So anything out there that sort of ratchets up people's fluency in physics, I'm all for it. Well, even if they didn't understand what the hell they were looking at.
Right. I was like, Matthew McConaughey, I think he's aging. I'm not sure. There's a thing with the daughter.
Yeah, the daughter and the thing. Yeah, so that we covered that. But let's get back to gravitational waves. You reminded me, I'd forgotten, that when we were on stage, we actually did a gravitational wave together.
The gravitational wave dance.
Dance.
It was, yes.
Yeah, I don't know if we have footage of that, but I hope not.
Me too.
I'm trying to picture it.
So, Nergis, remind everybody, we've heard the term gravitational waves or ripples in space-time. That's surely accurate, but I don't know that it helps. So how can you dig into that and unpack what's going on?
Yeah, so I think one of the ways we can think about that is it's very tempting to look out into space and think of empty space as a number of things that aren't true. Space isn't empty. Space doesn't do nothing. It actually has many, many dynamical properties, things that, like, it can curve, it can ripple, it can tear. And so that's really the wavy part of space-time. And the idea is that when we have objects that are massive, so they should have gravity, and if they just...
When you say massive, you don't mean a brick or a stone. You're talking about black holes.
Well, bricks and stones would do the same thing, except it would be just a much, much smaller effect.
And harder to measure.
Way harder
So
to
our
measure.
threshold is for what? I mean, our measurement threshold
Our
today.
measurement thresholds today are not even ordinary stars like our own sun.
Couldn't measure that.
No. So if we're looking for waves from these kinds of objects, there are more things like neutron stars and black holes.
So dense objects in the universe
objects,
where
exactly.
gravity is saying something.
Yeah, so objects that have so much gravity packed into a small volume that really the space around those objects is very bent.
Okay.
Have those objects tried Ozempic?
How do we end up doing a commercial for a pharmaceutical company and we're not getting paid for
We're
it?
helping the black holes slim down a little bit. They're very dense. They're causing waves and gravity. That's
Actually,
We don't want them to slim down.
for their work, but actually, isn't Hawking radiation a kind of Ozempic for black holes?
Yeah, it'll help them evaporate.
Yeah, so we got a little mechanism. So tell everybody about Hawking radiation.
So Hawking radiation, it comes about from the quantum mechanical properties of black holes. So the idea is that in quantum mechanics we have a phenomenon where particles and antiparticles can be formed out of photons, and then they can crash together and become photons again. And Hawking radiation
So
is
it's energy to matter back to energy.
yes.
E equals MC squared would prescribe how much of that is happening
Right.
in any moment. Okay.
right. And Hawking
E
radiation.
on one side, M on the other side. So we good.
and then C is speed of light.
Speed of light squared.
Yeah.
Squared, yeah.
Okay.
And so this is a phenomenon by which, as you create these particles, some of that energy can get radiated away. Where does that energy come from? It comes from the properties of the gravitational properties of the black hole. What happens?
So you're stealing matter out of the black hole and thereby taking away some of its gravity.
Yes.
Okay. And it just does that. And so it's a very slow version of Ozempic for black holes. That's what started
very,
this.
very
I just want to
slow.
finish it there. Right. Okay.
Yeah.
All right. So, Nergis, can I take you back to when I was 14? All right. I came to the Hayden Planetarium. Here's my office here. I became director of the planetarium. I came here as a
Not
kid.
at 14.
No. No, ultimately I became director.
Okay.
So I came here, and I beyond the space show that I watched at the time, they would have programs at night, which we still do. And with speakers would come in and give lectures on modern astrophysics. So I would come in for that. And one of them was on black holes. that's when I first learned that gravity moves at the speed of light. Okay.
You knew that when you were 14?
Well-
I didn't learn that till I was much older.
That's when I learned it.
15.
And then I thought about it, and I said, if gravity travels at the speed of light, then how does gravity get out of a black hole? And the answer was a little fishy to me. They said, well, there's a gravitational field that's always there. And it's a change in the gravitational field that moves at the speed of light. And I don't know if that's accurate, but that's what the dude told me. And otherwise, he couldn't get gravity out of a black hole where the black hole doesn't let anything get out, even the speed of light. And that the gravity moves at the speed of light. How's the gravity going to get out of a black hole?
I just don't think of it that way. I think about gravity as the geometry of space-time. And the black hole is part of that geometry. And the things that we can know about, and this is true for light as well, are only things that are outside the horizon of the black hole. So what I've always been taught, and I think I learned this maybe even from Kip Thorne, was that it's not meaningful to think about what happens inside the horizon because we don't even know if our laws of physics would hold there or not. And so when I think about gravity traveling at the speed of light, what's actually traveling at the speed of light is a gravitational wave, and it's only really meaningful outside of the horizon.
She dodged that one.
Yeah. We can't know what's in there, so who cares?
She totally dodged that one. No, that's good. That's an important distinction that physics had to mature into as a field to realize there are things that are beyond your knowledge, and therefore there's nothing you can say about it.
Right.
At all.
For now, who knows what other forces we might discover that would describe something inside that horizon.
Okay, but right now that's not happening.
Right.
Okay, so, but a change in gravity would then be a ripple, a change in that sort of thing that I'm feeling out there.
Right.
And we can just watch that at the speed of light. Because we'd say if we pluck the sun from the center of our solar system, you wouldn't know about it for 8 minutes and 20 seconds. You'd still orbit. We'd still feel the heat. We'd still feel the gravity. Everything would be normal. And then 8 minutes, 20 seconds later, we fly off at a tangent in the dark and freeze in interstellar space. Have a nice day. Yeah. How that's going to happen.
But those 8 minutes before are amazing.
Did Einstein, I don't know that I've seen the paper that did this. Did he predict gravitational waves?
Yeah, so Einstein, when he was developing the theory of general relativity, and this was the theory of gravity. So the thing so we all learn in school Newton's version of gravity. And Newton's law it's easy to understand. It's intuitive. It says you have two objects that have mass, and they're going to feel a force of attraction between them. And it was quite quantitative. He said the force of attraction will be proportional to their masses and inversely proportional to the square of the distance separating them.
It's very clean. That's a clean operation.
We teach it in very early sort of first encounters with physics, and it was quite successful. It told us about how orbits would work, and it also had pretty early on places where it didn't work perfectly. Now, what Einstein, when he was thinking about gravity, he kind of turned it on its head. And he said, well, look, gravity's not really a force. Gravity is the geometry of space-time. Big words. But he had a series of papers, 2 or 3, from 1915 to 1918, in which he sort of formulated this theory of general relativity. He wrote down what are now known as Einstein's equations. They look not that much worse than, say, Newton's law, except they're quite beastly. They're very difficult to solve. But part of that work was that he did ask the question, what happens if whatever object you're thinking of isn't just sitting still in space? What happens if it's moving, and not just moving at constant velocity? What happens if it's accelerating? And then out of his equations popped this wave-like object, which he called gravitational waves. And the other
I
thing was,
want stuff like that to pop out of my equations. Do you have equations where stuff pops out?
No.
look, me neither.
I'm still stuck on the wave part.
The wave part, okay.
Was he gravitational surfing?
They have a lot of analogies to that, because if you wanted to try and visualize what would this look like, one way that you could is you could think of space-time as the surface of a still pond. And you drop a big rock in the middle, and there's a wave that travels, a ripple that travels on the surface. It travels outwards from where you drop the rock. And if you were a little teeny tiny ant on a surfboard, you would surf that wave, right?
And the wavelength, so the distance between the crests,
Right.
would be related to how big was the rock that you dropped in.
Exactly, right.
Okay. So
Yeah.
when you measure gravitational waves with LIGO or whatever other tools available to you, you try to measure the wavelength of that so that you can infer what created that wave. Because otherwise, you didn't see the thing happen.
No, exactly right. So we measure a number of things. We measure the wavelength, which is the spacing between the peaks, in the successive peaks. We also measure the amplitude, which is how big, what was the height of the wave. And both of those things are changing with time, depending on what the source is. So by measuring sort of the shape of the wave,
As you go into it and as you come out of it.
as it passes by you.
Yeah, as it washes over the earth.
Exactly. And as you do that, you can you can infer some of the properties of the system that emitted that wave. Sort of like if you just saw the ripple at the edge of the pond, and you have to kind of measure the frequency of the wave, you have to measure the amplitude of the wave, you have to know something about the density or the viscosity of the water of the pond.
That's
and
right.
from
Because
that,
the medium, it would come through differently.
right. And once you have put those things together, without ever seeing the rock fall in the center of the pond, you can say something about the rock. And that's kind of what we're trying to do.
So that's very impressive because you get this measurement, and then out in the research papers, so these are two black holes of 30 times the mass of the sun colliding a billion light years away. I mean, that's badass to make that kind of statement.
It is. I think that the properties of the black holes are I can't think of too many things that are more badass than that.
I agree.
I have to tell you why. I mean, so, one of the first gravitational waves that we measured with LIGO were from these 30 solar mass black holes. And you know what these monsters were doing? At the time that they collided, they were moving at half the speed of light.
Whoa.
Okay. You are speechless.
I'm trying to picture it. I don't know if I can actually picture what that. I'm picturing a Godzilla movie where it's like a black hole with like little arms
Start
and
with
legs,
Godzilla.
and they're both fighting each other. But instead of the city, it's space. That's where my brain is going.
And instead of, moving at sort of human and Godzilla speeds, they are moving at the speed of light. The amount of energy it takes to accelerate a little electron in our sort of, experiments to the speed of light. And to think we do it with something that's 30 times the mass of our sun.
So there's no greater particle accelerator than the universe itself.
Indeed.
Ooh.
Is it making a sound when it happens?
No. And the reason is that...
But wait a minute. You guys put a soundtrack to that wave.
That's different than whether it made the sound.
Then get us out of that media ploy, because I always have to undo things that the media does or give context for it, because people say, well, if space is a vacuum, and because they knew that sound doesn't travel through space.
No one can hear you scream.
No, exactly. That's a legit call, right, for the movie, the Alien.
Yep.
So did you endorse this attachment of sound to it? How did you, as an educator and as a physicist, where were you on that?
Yeah, so, I think of it as there are many, many phenomena as scientists or as humans and observers that we can't directly observe. Let's take light. So we love to look at pictures of even astronomical objects where they're emitting X-rays. We can't see X-rays, so we color it blue. And we can see blue, and then the object looks blue, and we imagine that's an X-ray. And so when I think about sound, or the sound of these, waves, it's an encoding. It's a way of mapping it onto senses that we do have.
Okay.
Right? So that's how, because otherwise...
That's fair enough.
So, I mean, think about the way that we visualize a cell. We can't just look at a blob of stuff and say that, that's the cell. We've used microscopes, we've used ways of observing, and then we put together a picture.
We've enhanced our feeble senses
Exactly.
to gain access to the universe that would otherwise lay forever invisible in plain sight.
But it's dangerous because if you pick the wrong sound, then nobody cares. Like if you make a video of two black holes colliding and it goes boing,
Boing.
Yeah, exactly. You got to pick the right sound.
Something out of
Awooga.
a Tom and Jerry cartoon.
Exactly.
Awooga.
Bing, 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 bing. It doesn't work.
So with LIGO, all's well that ends well, but it didn't begin smoothly. I remember there were physicists called to Congress to defend the budget outlay to the National Science Foundation that was going to take huge chunks of money to pay for your laser toy.
Yeah.
How did you convince them you weren't building a Death Star?
Yeah, so a couple of things. It is certainly part of the history of LIGO that, so what I know of the history is that Ray Weiss and Kip Thorne, two of the founders of LIGO, Ray Weiss was an experimentalist thinking about how you might measure gravitational waves.
And he shared the Nobel Prize.
Right, and they shared the Nobel Prize. And Kip Thorne was thinking about the astrophysics. What would gravitational waves look like if two neutron stars or black holes collided? And they met somewhat accidentally in 1975. The story goes that they had to share a hotel room because one of their bookings got messed up. And then they were up all night conjuring up how one would make this measurement. And that's where the concept of this 4-kilometer long detector, 2.5 mile long detector, LIGO, was born.
What intrigues me here is at the time, because I remember, because I'm that old, there was someone at the University of Maryland, Joe Weber, who was building a gravitational wave detector. And it was a cylinder of aluminum with very highly sensitive servos, if that's the word, that monitored the position of this slab of aluminum. And if a gravitational wave washed over it, it would jiggle it in such a way that he would then measure it by way of these servos. So this method, conjured in the wee hours of the morning in a hotel room, is a completely different method.
Correct.
And maybe there's no way you could have detected it with a cylindrical slab of aluminum.
I think now in hindsight, we can say that would have been we haven't done that yet,
Yes,
right?
okay.
So it is true that Joe Weber at the University of Maryland had this big slab of metal, and it was instrumented with sensors that would see this big slab of metal ringing, just like if you hit a wine glass and it sort of rings a tone. So it would ring because of the gravitational wave that went through it. Now, it turned out that Weber's claim, so when Weber made the claim, a lot of people started to build similar instruments and to try to reproduce the measurements, and they couldn't. And eventually, people just didn't believe it.
If I remember correctly, he had a paper saying he had a measurement.
Right? He had a measurement, and if I recall correctly, the claim was, we have a measurement, and not only do we have a measurement, but it seems like the wave is coming from the center of our galaxy, which was sort of seen as a preferred location for some gravitationally heavy object like a black hole. But people just couldn't reproduce it. But what it did do is it really sparked interest in the topic. And so a large number of people started to build these, and they weren't making any measurement.
Not all null results are bad if they stimulate interest, is the lesson there.
I think that's right. And even in Weber's case, though, eventually it turned out to be incorrect claims. He invented some techniques that even to this day we still use. So
okay, you mentioned something very important about science. One researcher's result does not make the truth.
Yes.
You need verification.
Yes.
Because anything could happen. They could be biased. The current could have fluctuated. Anything could have happened in one case. But if you have 2, 3, 4, and if they give the same result, you got something good. If nobody can match the result, it's time to move on. That's
right. And in Weber's case, I think it was even more interesting because he had 2 of these bar detectors. And it was only when people built 3rd, 4th, 5th, and they were built with slightly different technologies, and perhaps even with slightly different expectations, that it was understood that no one was reproducing what Weber was saying.
So now in LIGO, when you made your grand announcement, 2 black holes colliding, why should we believe you? Because
question.
is there another LIGO to check what you did?
Yes.
Oh, well, there it is.
How many of these lasers are there?
Okay. So, yes, there is. Next. We're done there.
Nice.
No, there was foresight there, of course. The
Right.
the LIGO facility I visited was in Louisiana, outside of New Orleans, but you would have a whole other one. If that one LIGO facility makes a detection, you would presume and expect another LIGO to make the detection as well.
Correct.
Not necessarily in the same moment, separated by...
Almost certainly not in the same moment, because there's another LIGO facility in Washington State, east of Seattle. And you can think about sort of, if you think about a wave that's coming through the Earth, a gravitational wave does that. If a gravitational wave is emitted by some distant source, light is actually quite difficult for astronomers, because light coming to us interacts with everything in between. Gravitational waves just pass through most things.
Oh.
So they are quite
You
useful.
have a pure expression of what happened at its source.
Yes, but it's a double-edged sword, because by the same token, it doesn't interact very strongly with our detector either. So it's really pretty darn
Be careful
weak.
what you wish for. Right.
This gravitational wave sounds rude.
Wait. So the one in Washington, it's Hanford, I think. Is that the one?
Yes, in Hanford, Washington.
Washington, which I think used to be a place where they purified plutonium.
Yep.
Yeah. So are you giving emotions to the gravitational wave? You declaring it's rude?
Yeah, the gravitational wave just walks through the party, says hi to nobody.
Nobody,
and then
right.
leaves.
Yeah, so that is one of. So if you ask one of the things that we haven't observed with gravitational waves is gravitational waves from the very early universe, say right after the Big Bang. And when we think about what we know about the Big Bang,
But just to be clear, you haven't observed them because you don't have the capacity to do so yet. Not
yes,
because
our instrumentation just isn't sensitive enough.
Okay.
Yeah. So if you think about what we know about the Big Bang, what we know comes from light. Now, the light that we see from the Big Bang, this cosmic microwave background, actually comes to us from 400,000 years after the Big Bang. Now, what happened before that, we can't tell, because the universe was so hot and dense at the time that the light couldn't escape. Now, what does that mean? It's exactly what you were saying, Harrison. So the light is like going to a party with an extrovert, and you say, honey, I'm ready to leave, and it'll be an hour before you leave the party, because they're going to stop, they're going to say hi to people on the way to saying bye to people.
and top off their drink.
Yeah, exactly. And they're not coming. Gravitational waves from the early universe have been streaming to us. If we could measure them in the LIGO band, they would be streaming to us from when the universe was 10 to the minus 22 seconds old. And the reason is just what you said. They're like going to the party with the introvert. You say, we're ready to leave. And you're lucky if they'll say goodbye to the host.
Right. So this distinguishes our access to the early universe from what our normal telescopes can bring to us,
Right.
which is this 400,000 year barrier, really.
Right.
And the gravitational waves, which just plow right past that. They don't even care. They're moving right along.
Right. And so if you want to see the earliest moments of the universe, gravitational waves are your friend.
If we want to make them more sensitive, do we have to have bigger lasers?
That's a piece of it, but there's lots of other things you got to make better too.
So that kind of dovetails to a bone I have to pick with you people,
Do tell.
you quantum people. I'm in conversation with Kip Thorne, and I verified, because I'd read this, but he's the man. And I said, you have all this apparatus, 4 kilometer long beam that reflects and they recombine. You look at a phase shift and look at a jiggle. And I said, how big is that jiggle? How much did this apparatus move by virtue of this wave passing across? And it is the width of 1/20th the diameter of a proton.
When it's cold, when it's nice outside.
No, that's too big.
Too big? Wait, so all right. So let's just speak more broadly. A fraction the diameter of a nucleon of an atom, okay?
1,000th.
Okay. So you want to make sure nothing else is responsible for what you're about to measure. Otherwise, you're measuring the wrong thing. And when I visited they were telling me if somebody's walking down the street a mile away, those vibrations can be detected in that. That's exactly how they described it. But they see all vibrations, so they have to isolate the experiment from anything that could be happening from the outside. Okay? So then you isolate it, and then you put it in a vacuum so that air particles are not bumping into it. So now it's there. But then it is at a temperature. It's not at absolute zero. So at any temperature, everything is vibrating. And even if you tamp that down, there's always a quantum uncertainty about the position of a particle. Heisenberg told us this, okay? So if you want to know exactly what a particle is doing, there's an uncertainty to that. So how are you making measurements that are smaller than the quantum uncertainty allows? And we had this conversation, and Kip Thorne said, well, we did blah, 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 and we did this. And in that way, we cheated the quantum laws. And I think, no. Then it's not a law if it bends at your will. So what was he talking about?
Yeah, we do that.
No! That's not an answer! So this is like Invasion of the Body Snatchers. Yes, he's one of us.
I was thinking Freeze like one of us.
We both can bend the rules of quantum physics. So, okay, for those of you who have such powers, please explain to me.
Yeah.
In as plain as English as you can.
Yeah, so I can try to do that. So what quantum mechanics tells us is that if you measure two particular properties of a particle, and in one example would be the energy of, let's talk about photons, because it turns out in LIGO at the moment, we're limited by the quantum mechanics of the light. The quantum mechanics of the mirror isn't yet a problem because the mirrors are still moving more than their quantum properties would allow. Okay, so let's talk about the light. So the quantization of the light says the light has two properties. Light's made up of photons, and if I want to make a measurement of that, I want to know two things about it. What was the energy of the photons that I'm measuring, and when did they arrive on my detector? And you can't know those two things at the same time with infinite precision.
With perfect knowledge.
Exactly, with perfect knowledge. But you can know one of those properties very, very well if you allow the other one to be very unknown. That quantum mechanics allows you to do. And that's the trick we play. So if we are interested, as we are in our measurement, measuring the phase of the light wave.
The phase would be because you have two light beams,
right,
and you have to see how they match up.
That's right.
Because if they match up perfectly, nothing happened to one relative to the other.
Right.
Gotcha.
But if a wave washes over, then one jiggles a little differently, and the waves don't match up. You'll see the okay. So
right.
That's
exactly right. So say if you're interested in measuring the phase, then what you can do is you can create light with properties where you let the amplitude or the energy of the wave be very unknown, but you've traded that off for precision in the phase. And we have learned how to make instruments that can do that.
Damn.
So they're instruments that increase uncertainty.
In one
variable.
That's right.
And
reduce it in the other variable. And that's really important. If you were reducing the quantum uncertainty in both variables at the same time, you would be violating the laws of physics. But that we're not doing.
Okay, you're just bending the laws of physics.
Yeah. So they're not breaking the laws at all.
No, it's a loophole.
I like to say...
This is a quantum loophole. Admit it.
No.
Oh, she got angry. She got some attitude on that one.
So much for increasing the uncertainty.
I call it manipulating the laws of quantum physics because we can't violate them. And loopholes are things that are just usually things you haven't thought of.
Yeah.
Whereas this we've thought of. We're deliberately doing this. And, so that's the kind of thing.
So it's not a problem if you don't know at all what the...
So there's a price to pay.
Yeah.
The price to pay is, look, if you're interested in measuring the phase, and if by accident, because your measurement apparatus isn't perfect, you start to collect a little bit of information about the amplitude, it won't work for you anymore. Because remember, the amplitude is now very, very noisy.
Wow. Okay.
So this is what we do. We reduce the noise in the quantity we're most interested in measuring. We stuff it into the quantity we're trying not to measure.
Okay.
And then we try to do that as well as we can.
Grabbing quantum physics by the horns
Yes.
and making it bend to your will.
You know, almost. We call it squeezing. We squeeze the light.
Let's get the picture of this now. You have two beams.
Yeah.
They're at right angles, I presume.
Yeah.
Yes. And the round trip is 8 kilometers. Is that right?
Yeah.
Okay. And so it takes time for the very measured time for the light to do that. This is a single laser beam of light that has been split, correct?
It has been split. And not only does it go 4 kilometers down and come back, there's an added complication, if you will, which is that in that 4-kilometer span, we have a pair of mirrors that are facing each other. And just like when you put your own head between two mirrors and you see multiple images, the light is bouncing multiple times between those. It's a way of increasing the path length, if you will.
All right.
So it bounces, in our case, in LIGO's case, about 100 times.
Okay. But then it has to come back through to recombine.
Yes.
Okay. So you have your magic ways that it goes up and back 100 times. Then at some point, the light has to come back through and not reflect back.
Correct.
And then you compare the waves of the light.
From the two arms, yeah.
So that's the shift. So how much different would one wave have to be from the other to be the gravitational wave, to be the effect of the gravitational wave?
Yeah, so the way that you can think of it is that the output of our instrument, we're measuring, you think of the light as 2 sine waves, one from each arm, and we arrange the distances such that the 2 light waves cancel. So the peak of one sits on the trough of the other, and in the ideal case, you would see no light, 0, right? And then if one arm is slightly different in light than the other arms, then they don't perfectly cancel, and now some light sort of trickles out.
Ooh, brilliant.
Right, exactly.
I should get a Nobel Prize for that.
That's pretty good.
They already did.
You're tied with Einstein.
So it's always better to see a signal where there isn't otherwise a signal than to measure the difference between 2 large signals.
Yeah, if you try to measure a tiny difference in a big number, it's really hard to measure.
Very hard.
But you start with something that's very close to...
error-prone, too.
Right.
Yes.
You start with something that's very close to 0, and now you get anything, you got something.
Wow.
So that's what we do.
And how strong is that extra signal compared with the amplitude of the waves to begin with? So what fraction of that amplitude is it?
Yeah, so that's sort of a technical detail, because you start off with, 100 watts of laser light. And by the time
That's a powerful laser, by the way.
that's a very powerful
I believe it.
laser, particularly if it's a laser that's also, as quiet, noise-free as ours.
What is my laser pointer?
Your laser pointer is like a milliwatt.
Yeah,
Oh, okay.
milliwatt.
Wow. Okay.
Yeah,
So
a
this is,
really bright one might be...
A few thousandths of a watt.
Right.
gotcha.
And this is 100 watts.
So this is 100 watts at the laser, and by the time the light has bounced between all the mirrors and so on, at any given instant in time, you could have, hundreds of kilowatts of power circulating in the instrument. But at the time that we detected at the output, we're trying to go for, very little light, close to 0. We're measuring something around of order 10-ish milliwatts of
10
light.
milliwatts. Okay.
But,
relative to the hundreds of thousands of milliwatts that are moving around.
That's right. The more interesting question is you can think about the output of the interferometer is itself just as it's a sinusoidal function. And so the way I like to think about it is we try to park ourselves at a trough. And
the bottom.
At the bottom. And then we're asking, what is the smallest amount of light that you can distinguish, resolve? And that is how much of phase or distance, path length you're resolving. And so that's the number that corresponds to a path length difference of 10 to the minus 18 meters.
Which is the fraction of the diameter of a proton that you were
thousandth the diameter of a proton.
Crazy talk.
Yeah.
And so she slipped in a nice term in there. I want to pull that out. She mentioned interferometer. Okay.
Ooh.
That as a device had to be invented. And it was invented at the turn of the century, the previous century, by Albert Michelson and Morley.
Morley.
What's his first name? I don't remember his first name. The famous Michelson-Morley experiment. They invented it to measure the speed of light. So the first truly accurate measurement of the speed of light was by Michelson and Morley using an interferometer where they had waves that either line up or they don't, and the amount that they don't line up will give you information about the speed of the light that they were measuring. So, I mean, it's a hugely powerful. So they got the Nobel Prize for inventing that device.
It feels like they're just giving these things out.
No, stop.
I think this is the third one we've heard about today. Just handing them out like candy.
So just I'm just impressed by how all this comes together.
I think it's just a reminder to us that every discovery we make is built on everything that came before, right? Because we've talked about so many things that were invented 100 years ago that were important to the discoveries we made in 2015.
All right, so take us out with your prediction of what discoveries await us to take the physics we now know into a new place, or what new physics needs to arrive to take our understanding of the universe to a new place.
Yeah, so I would say at the moment, the kinds of objects, astrophysical objects we've seen so far have been collisions of pairs of black holes or pairs of neutron stars, or maybe neutron stars and black holes in the same binary system. And those were predicted. We kind of expected them, but even that has given us mysteries. Like, I'll give you an example. We've seen black holes that are around 100 solar masses. We don't know how nature forms those, because if they're formed in the same way as black holes that are 20 or 30 solar masses are formed, stars don't do that.
Right. It means we don't understand how stars are born.
That's right. Or die.
Right.
Right.
I always thought
Exactly.
it's like you pick up an instrument and you practice a lot. That's how stars born.
Oh. Is that how that works?
I think there's been 3 films of that.
Yeah, they keep making the films, right?
They keep remaking
they
that
keep
one.
the stars born.
What I'm saying is we've had 3 films to learn how a star is born.
But let me just remind you that movie stars are called stars because we had stars first. Okay, we came first.
Not because they're filled with gas.
Hot gas. They are named after objects in the universe, not vice versa, just to be clear.
But
Makes
Neil,
sense.
I think this is a good idea for you. I think you need to make the ultimate A Star is Born movie about real stars.
Oh. If we're going to make the movie again, just make it right.
Yeah, I agree.
I'll be the one in love with the stuff.
Well, thank you for enlightening us here with your insights and your expertise and your deanship.
Oh my gosh.
What I'd like to do is sort of take us out with a cosmic perspective, if I may. This is the part where I just talk to camera and you just pretend like you're paying attention. Once again, we are exposed to major modern discoveries in science, physics in particular, that was enabled by creative thinking that preceded it, creative engineering, improvements in computational speed. These things happen. Yeah, you can say, I got a really fast computer, and you can be praised for that, but maybe someone can use that for something that they could not have solved before. I have a new idea about how black holes work. Well, let others know about it, because somebody could have another idea about how to apply that to a discovery we're not even thinking about now. And so this interconnectivity, this interdependence of cosmic discovery on these multiple frontiers is how science works. People ask, are we approaching the end of science? Well, if you think everything that will ever be discovered has been discovered, then you'll probably think that. But my read of the history of this exercise tells me that if you think science is about to end, it's because you're not creative enough to imagine where else it could go. And look at all the dangling bits and pieces of all the scientific frontiers and how they might one day come together with a next generation Einstein to take us into the next millennium of cosmic discovery. And that's a cosmic perspective. So, Nergis, thanks for coming back to StarTalk. We dovetailed another talk you were giving at NYU, sister institution downtown. Thanks for fitting us into your day. And again, it's Mavalvala. Yes,
It
I
is.
did that
It is.
correct.
Thank you.
And
Thanks
Harrison,
for having me.
great to see you again.
Same here.
Good
same
to hear about your show.
Thank
People
you.
can find you at Harrison Greenbaum.
.com at Harrison Comedy on social media.
You got it. Neil deGrasse Tyson, your personal astrophysicist. As always, I bid you to keep looking up.